Proper grounding is critical to powered line transmission towers. These towers are highly susceptible to lightning strikes, which can result in dangerous flashover conditions. To ensure your transmission lines are adequately protected from this risk, it's essential to be able to accurately measure how well each tower is grounded, as well as test the quality of the overhead ground conductor connection. AEMC's GroundFlex Field Kit is a robust and versatile system for testing the grounding of power line towers. At the core of this kit is the Model 6472 ground resistance tester, operating in conjunction with the Model 6474 GroundFlex adapter. Other kit components include sensors, electrodes, and all required leads, connectors, and wiring. In this video, we briefly describe how to use the GroundFlex Field Kit to test a tower. We start by explaining how to set up the kit to obtain static readings such as passive resistance and leakage current. We then dynamically test the total tower resistance, initially at a baseline frequency, and then via a sweep from low to high frequencies. Our test subject in this video is a four-legged lattice tower. However, the GroundFlex Field Kit can also test monopoles, H-frames, and tri-leg towers. The first step is to set up the kit's test environment. This involves installing the GroundFlex sensors on the tower's legs, attaching the voltage and current probes, placing the grounding electrodes, and connecting all components to the GroundFlex Field Kit. Start by connecting the Model 6472 and Model 6474 instruments together using the connector supplied with the kit. The Model 6474, which operates on power supplied by the Model 6472, serves as the primary interface for the four GroundFlex sensors used in this test. These sensors are Rogowski-type coils. Next, install the GroundFlex sensors around each leg of the tower. A sensor can be looped around the leg up to 4 times. The more loops used, the more precise the measurement. All sensors used in the test must be looped the same number of times. Note that each sensor is labeled with arrows. For all sensors, these arrows must be pointing in the same rotational direction on each tower leg. In this test, we will loop each sensor twice, counterclockwise. We then connect each sensor to the Model 6474 and set the sensor turn dial on the instrument to 2. Be sure that the sensors are connected to the instrument in sequence. For example, in the diagram shown on the screen, we have designated the sensor in the upper left as number 1, with numbers 2 through 4 following in a clockwise sequence. Next, set the input dial on the Model 6474. This indicates which tower leg or legs you want to test. In this instance, we would test all 4 legs together, so turn the dial to the 1, 2, 3, 4 setting. Finally, set the sensitivity dial on the instrument to 1 to establish measurement sensitivity. Locate the green and black test leads. The green lead is used to inject current into our test setup. The black lead is used for voltage measurement. Both leads must be attached to a tower leg next to each other at a point higher than the GroundFlex sensor. This can be any leg as long as both probes are connected to the same leg. Connect the green lead to the Model 6472 instrument by inserting it into the connector labeled E. Insert the black lead into the connector labeled ES. Now install the ground electrodes. The electrodes are placed on opposite sides of the power lines, ideally at a 90-degree perpendicular angle to the direction of the lines, as shown on the screen. If this is not possible, be sure to locate the probes at least 30 degrees that are parallel with the lines. Each electrode should be placed at least 50 meters or 150 feet from the lines. Connect the electrodes to the Model 6472 using the red and blue leads that come with the kit. Ideally, the lead wires should be rolled out completely to avoid any inductance generated in the coils by the proximity of the transmission lines. We are now ready to take measurements. We'll start by obtaining static data that does not require an output current. This static data will help identify whether or not we need to make any adjustments to our setup before performing dynamic tests. Turn the dial on the Model 6472 to the ground flex setting. The instrument performs a series of self-calibration tests, during which the red overload LED light on the Model 6474 may light up briefly. When this is finished, check the row of icons at the top of the display screen and ensure they match your test configuration. In the upper right corner is the icon indicating the number of tower legs we're testing. In this case, we're testing the vector sum of all four, as indicated by the dial on the Model 6474. This should also be reflected in the icon. The next icon on the left indicates the number of times we looped our ground flex sensors, which in this example is 2. The next icon to the left indicates measurement sensitivity. In our example, this is 1, as we said earlier via the sensitivity dial on the Model 6474. If any of these icons indicate a setup discrepancy, make the appropriate adjustments now. Note that if the red overload light remains lit and the Model 6472 buzzer beeps, this indicates that the current in the ground flex sensors is too high for the selected sensitivity. If this happens, set the sensitivity dial to 1/10. If the condition persists, remove one loop from each sensor wrapped around the tower legs. Press the display button once on the Model 6472. The screen shows 2 important values. The first is labeled U sub out. This is the output or injector voltage we will use to perform our tests, which in this case is 32 volts. The second is the baseline frequency that will be used. In our demonstration, this is 128 Hz. A second press of the display button provides us with our first measurement, the actual passive resistance of the 4 tower legs in combination. As you can see, this is slightly over 3 ohms. Another press of the display button shows the voltage between the black output terminal, attached to the instrument via the ES connector, and the electrode connected to the instrument via the blue S connector. This value is labeled U sub SES, and in our demonstration is around 0.45 volts. If the measured voltage exceeds 0.1 volt, as our measurement does, this screen also shows the frequency of the detected voltage. This is the same as the frequency of the transmission lines, which in North America is usually 60 Hz. It is also common under some conditions for this to be 180 Hz in a 3-phase system. Pressing the display button again shows the voltage between the green E output terminal and the electrode connected to the instrument via the red H connector. This voltage, labeled U sub HE, should be within a volt of the U sub SES voltage, as is the case here. This indicates that both electrodes are placed far enough away from the tower so that they are not affected by the tower leg's potential shells of influence. If the voltage readings are below 0.1 volt, this likely indicates that the tower's transmission lines are not in service, or that the overhead ground conductor is completely corroded or not connected. In this case, the total tower current will also be close to 0. If the difference of the reading exceeds 1 volt, move the electrode with the lower reading further out from the tower and take a new reading. Too large a voltage difference between the electrodes may invalidate any results we obtain from our subsequent testing. Another press of the display button shows the leakage current flowing through the tower to the ground. In our example, which is measuring the leakage current for all 4 tower legs, this is around 150 milliamps. You can also measure the leakage current for each tower leg individually by turning the input dial on the Model 6474. The sum of the individual leakage currents for the legs should approximately equal the leakage current measured for all 4 legs simultaneously. If this is not the case, for example, if the measurement of the combined legs is near 0, while the sum of the individual legs is significantly higher, the overhead ground conductor may be disconnected from the tower, perhaps due to corrosion, and should be inspected. Now that we have obtained static measurements, we can perform a dynamic test. To do this, press the display button to return to the main display screen. Then press and hold down the Start-Stop button on the Model 6472. When you do this, the instrument will beep once. Continue to hold down the button until the instrument beeps a second time, and then release the button. The instrument now performs a test using a test voltage of 32 volts and a frequency of 128 Hz. During this process, an indicator consisting of 3 rotating arrows appears. This remains on the screen until the instrument completes its measurements and calculations and displays the results. When this process is complete, the values are displayed. At the top of the screen is the total tower resistance. In our test, this is the resistance for the combined 4 tower legs, which is around 4 ohms. A properly grounded tower should produce a measurement below 15 ohms and ideally below 5 ohms. Note that this screen also shows the resistance measured between our output probes and ground electrodes. For each electrode, resistance should be below 1000 ohms, as is the case here. Resistance higher than 1000 ohms can call into question the integrity of the measurement results. This is because resistance determines the test current, and too low a current makes obtaining reliable results difficult. In this situation, an indicator consisting of greater than and less than symbols may flash, informing you that the measurement may be unreliable. If the resistance for either electrode exceeds 1000 ohms, you can moisten the soil around the electrode by pouring water on it, and then retesting. You can also connect additional auxiliary electrodes to each test electrode. These auxiliary electrodes should be placed in parallel with the primary electrodes at a distance of approximately 2 to 4 times the depth of the primary electrodes. We will now perform a sweep test. As noted earlier, our initial test was at 128 Hz. In the sweep test, a range of frequencies will be used, from 41 Hz up to 5078 Hz. To set up a sweep test, press the button labeled HZ Options. Then press the right arrow button until the word Sweep appears in the display. To start the test, press the Start-Stop button once. Unlike the earlier test, you do not need to hold the button down until the instrument beeps a second time. To establish a baseline, the Model 6472 initially performs a measurement at 128 Hz. It then cycles through the range of frequencies from lowest to highest. Note that since we are measuring inductance rather than resistance, the measurement increases as the frequency does. The results appear in the display screen. This concludes our quick demonstration of how to use the GroundFlex Field Kit. Note that the testing described in this video represents just a few of the many features and capabilities of this kit. For additional information about the GroundFlex Field Kit, consult the AEMC website. And be sure to visit our YouTube channel for additional instructional videos on other topics in electronics, including how to use the many products provided by AEMC.